done the same. Excellent. Okay, so we got another 30 seconds. People should run and grab those last snacks and coffee refills and whatever else you're doing on a Monday afternoon. All right, well, it is 4 o'clock. So let's go ahead and get the event started for today. So let me begin by welcome everybody back to the SMU Physics Department Speaker Series for Fall 2020. We are beginning October, which the theme of the month is Probing the Unknown, and we're beginning the month, as always, with a general interest colloquium. So this should be of sort of broader interest than the seminars that we've been having for the last 3 or 4 weeks since the colloquium at the end of August. In just a moment, I'm going to hand things over to Professor Pavel Nadolsky to introduce our speaker, Dr. Tim Hobbs. But before we get started, let me just say some of those usual reminders here at the beginning. So first of all, a reminder to our audience on Zoom that we've got the mics all muted except for the hosts and co-hosts. So if you want to ask a question, you need to write the word speak in the chat window, and you can do that during the talk, and we'll interrupt Tim at the next appropriate kind of boundary, like a slide change, or you can wait and do that at the end to queue yourself up for a question during the Q&A. And you'll only be able to speak when unmuted and called upon by a moderator. So don't be surprised if you start talking, but we don't hear you if your mic is still muted. That's all controlled by the co-host and the host. And just as a warning to everybody, this event is being recorded and simultaneously live streamed on YouTube. So let me now welcome Professor Pavel Nadolsky to introduce today's speaker.
Well, thank you very much, Steve. It's my great pleasure to introduce Dr. Tim Hobbs, who is an active member of our SMU group of theoretical physics. Tim is an expert in models of composite subatomic particles, such as protons and nuclei. He received his undergraduate degree in physics and mathematics from the University of Chicago. Then he earned a PhD in particle and nuclear theory in the Nuclear Theory Center at Indiana University. He then worked as a research associate in the nuclear theory group of the University of Washington in Seattle. Then he arrived to SMU as a postdoctoral researcher. Recently, Tim became a research assistant professor at the Illinois Institute of Technology in Chicago, and he has been also elected a member at large of the APS group on Hadronic Physics. So Tim is playing a very active role in our analysis of the proton structure and in making predictions for the major experiments such as the Large Hadron Collider. In addition to his activities in particle theory at SMU, Tim received a prestigious fellowship to lead the physics studies for the new facility planned at the Brookhaven National Laboratory called the Electron-Ion Collider. So this is a very important experiment that will provide unique new measurements related to the structure of the hadrons. And so today our colloquium will be dedicated to this fascinating topic. So Tim will introduce us to what the Electron-Ion Collider, or the EIC, could do, and discuss importance of this field for not just for studying the protons, but also for the particle physics in general. So with this, I invite Tim to begin the talk.
Excellent. All right. Yeah, thank you so much, Pavel. Thank you so much, Steve, both of you, for the kind introduction and the opening remarks. And in fact, let me share my screen. That's an important detail. Yeah, so indeed, this talk, oh, I lost the screen. Okay, sorry about that.
Oh, no problem. We see it again. Looks good.
Okay, good. Yeah, so indeed, this talk, I hope to do sort of two things with this talk, and let me also extend a greeting to anyone who might be joining us from other departments outside physics. So my hope is to do my best to try to bring everyone along as much as possible. And indeed, the idea is that this is meant to be accessible to students, for instance, and so please don't hesitate to ask questions. My idea with this talk is to sort of tell a story, I think one that should hopefully be familiar, I think, to at least a good number of you, but at the same time, perhaps told from a somewhat different angle than might be familiar to everyone in this audience. And what I hope to do really is to highlight what goes on in this field of hadronic physics. What is it? What are the open problems and challenges in this field? And really, why should you care, especially if you're a physicist? Especially if you're the type of physicist at a place like Southern Methodist University, whether you're, say, a particle phenomenologist, whether you're hunting for dark matter, whether you care about details of nuclear structure, all of these various questions. What I would like to put to you is that hadronic physics, this field, really occupies a kind of central ground among all of these different questions and is very pivotal. And in fact, you could think of it in a way as a kind of bridge that plays a unifying role, connecting physics at lower sort of medium energies to activities then at high energies, at the so-called energy frontier, as we like to say on the particle physics side of things. And so these various images at the bottom are meant to in some way kind of encapsulate or symbolize that connection, that this field and its future, the Electron-Ion Collider, as Pavel already gestured at, plays a role perhaps in connecting activities sort of toward the medium energy side of things at places like Jefferson Lab, going toward the high energy side of things at places like Fermi Lab or at the Large Hadron Collider, for instance. So I hope to give you some sense for what is going on in this field and why you should care, basically. That's sort of the goal. So what is hadronic physics? Without waxing too poetic, the way I like to think of it is really it's the science of the visible world, right? If I think of fundamental questions that humans have been asking for literally millennia, questions like what is life, what is the origin of the world, of the universe, I can't think of many other questions that are more fundamental than this one. What exactly is all of this stuff around us, this visible matter? What is it essentially? What is it at its core? And so that question, I think, is about as old as science itself, really. And the story of that question is indeed, I think, a story of sort of successive leaps to smaller and smaller length scales. And I've tried to give you a sense for that with this progression of images, basically, that obviously has a telescoping sort of nature in that it sweeps over, obviously, a huge amount of human intellectual history. The earliest incarnation of this question, at least in the Western civilization, really goes back to people like Democritus, of course, who were interested in trying to find a kind of terminus to this stream of length scales. But what exactly, if I start cutting visible physical matter that's around me, the idea is that at some point I must reach a termination in the stream. I must get to something that is fundamental, or you could read that to mean indivisible, something that cannot be further subdivided for things to have basically physical substance. This is the idea. And it's not actually an unreasonable way of posing the question or thinking about it. It sort of languished for quite a long time before being picked up with the dawn of modern science, like people like Dalton, the emergence of really modern chemistry and the molecular idea, which really brings one to the scale of, say, billionths of meters, say, being governed by the relevant dynamics there. But then things really got interesting, and the birth of this field really began to emerge, depending on how you count, as recently as about 100 years ago, roughly speaking, with Rutherford's discovery of the gold nucleus, which begins to bring one to the threshold of sort of the nuclear scale, right? Something like tens of femtometers, basically, as we would say, tens of 10 to the minus the 15 meters. It was not that long thereafter that actually Chadwick finally discovered the neutron, circa 1932, which really brings us to the threshold of what you could call hadronic physics, the hadronic scale. That is, particles that are governed by a scale of what we would call the femtometer, a Fermi, 10 to the minus 15 meters. So circa 1932, for all anyone might have known at the time, that could indeed have been the limit. The hadrons, like the neutron or the proton, for instance, that were discovered at that time and identified, could very well have been indivisible. They could very well have been the termination of that stream. But the question very quickly emerged, is that actually the case? Do things like the neutron or the proton or other hadrons, do they have some substructure to them? And what we learned actually very quickly, and what our predecessors learned, is that there were stubborn features of things like the proton that suggest that they are not actually the end of the story, basically, as far as what is making up visible matter around us. And that essential information really began to emerge in the 1950s with a series of pioneering experiments at the Stanford Linear Accelerator at SLAC at Stanford by people like Hofstadter, who measured a quantity we call the elastic form factor of the proton. And for the students in the audience who might not be as familiar with this terminology, I like to think of the form factor as essentially a quantity that tells me if I take an object like a proton and sort of whack it as hard as I can with a defined sort of amount of momentum, sort of transmitting a defined quantity of momentum, what is the probability that it remains entire, that it essentially remains a proton? So experimentally, what one would do is you would take something like a beam of electrons and impinge them on a proton target, and then in the final state, sort of downstream, try to identify an electron and a final state proton. And the idea is essentially as I dial up the energy, essentially in that scattering experiment, if in principle the particle is not fundamental, if it is squishy and made up of some basic constituents inside, then you would expect naively the harder I whack it with my electronic hammer, the smaller and smaller the probability that it remains whole, or put the other way, the greater the odds that it essentially disintegrates into whatever it's made of. And essentially that's exactly what Hofstadter and colleagues observed in the 1950s. They measured this electron-proton scattering form factor and observed that essentially the fall off in this quantity was much, much too fast compared to what was expected, and indicated that there was essentially some internal guts to this object, that it had some internal substructure. That's one important element of the puzzle. More or less contemporaneously, at the same time, more or less, there was a proliferation of other particles that were very quickly accreted and observed, if you'd like, the particle zoo. And they have very strange names that some of you may or may not have heard of, and they can be arranged in very, very intriguing fashion. So for instance, this object at the bottom left is the collection of baryons, for instance. There's the proton and the neutron that I just mentioned, which have a zero intrinsic strangeness, which is a degree of freedom. And you could also arrange these various particles according not only to that strangeness degree of freedom, but also to their electromagnetic charge or their electric charge. So for instance, while the neutron has zero net strangeness and zero charge, the proton similarly has zero net strangeness, but a charge of +1, for instance. That is exactly opposite the charge of the electron. But what was found is that there are all of these other particles, things like lambdas and neutral sigmas. These particles have this property called strangeness, and they can be arranged in this sort of group theoretic fashion. At the same time, there's another family of particles, the so-called mesons, which I'll give you a bit of a sense for in a moment, which can similarly be arranged in this subtle fashion. Why this is interesting is because the suggestion is that there are some internal degrees of freedom, as we would say. These particles are made up of something that can be sort of rearranged or reconfigured, not unlike the periodic table, for instance. And in that fashion, you can build up these various different hadronic particles with different properties. That was another clue that there was something going on inside these objects, that there was some internal degrees of freedom. So these two things were really essential bits of the puzzle. Not that long thereafter, after all of this was found, by the 1960s, there was another series of pioneering experiments, again at SLAC, the so-called SLAC MIT experiments, performing something not totally unlike the elastic measurements I just mentioned, but in this case, looking at something called inelastic scattering. It's very much like what I just said, but in this case, you might scatter an electron on a proton and not look for the final state proton, but just identify the recoiling final state electron that's been scattered off. And in particular, the process that's relevant is the so-called deeply inelastic scattering, where basically what I can do is, in principle, if there are these internal degrees of freedom in the proton, I can basically excite them and knock them out of this object. And I can do this in a way that I can study what we would say are the incoherent properties of this proton. And remarkably, what was found in the 1960s is that unlike what we saw with the elastic form factors, where as I whacked something with sort of higher and higher energies, there was this very rapid deterioration of the cross-section, as we say. something just the opposite happened. In this case, what happened is you would scatter with higher and higher energies, and basically these inelastic cross-sections exhibited an intriguing property called scaling, which is that the reaction became more or less independent of the scattering energy. And this is something that people like Jim Bjorken around that time successfully explained in terms of basically point-like constituents, things called protons by Richard Feynman. And the idea is that as you get to this very fine length scale in this deeply inelastic scattering process, you begin to basically resolve very, very, very fine length scales inside the proton. And you can actually begin to see something that looks like a hard core, right? You begin to see something that looks not unlike the elastic scattering that I mentioned before. And the indication is that the electron is not seeing the proton as a whole, but actually these point-like quark charges embedded inside. And this is really what brings us to the quark scale in these kinds of measurements and reactions. So a look at how this is done, I already said in words on the last slide, what the process is deeply inelastic scattering, the so-called DIS. I'll be mentioning this a number of times in this experiment. And why it's a favorable way of proceeding is that it has a kind of cleanliness, basically, and is depicted in this sort of cartoon at the top right. What one is doing, in fact, is an electron comes along and sort of streams by something like the proton and exchanges, in this case, a neutral current made up of either the photon or something called a Z boson, which is then exchanged and encounters things like the quarks inside this object. These are these point-like charge cores that I just mentioned. Now, for the more sort of technically or mathematically minded in the audience, basically the mathematical description for this process can be written down in a fashion that's diagrammatic. And the essential quantity is the cross-section, and what can be unpacked from it is an object we call the hadronic tensor. It's this sort of blob in this schematic diagram for this process. And the essential thing for this talk to understand is that there is a systematic mathematical procedure to then unfold from this blob, which encodes basically how these quark fields are correlated inside the proton that basically encounter this exchange electromagnetic field. That object can be unpacked and expressed in terms of so-called structure functions, or for the sake of this talk, parton distribution functions, the so-called PDFs that I imagine many in the audience perhaps have heard of. These PDFs, what they are, they're essentially probabilistic statistical distributions. So the PDF in this expression is related ultimately to the cross-section in a mathematical fashion for this deeply inelastic scattering process. And basically it encodes the probability to find in the moving proton a specific type of quark labeled Q carrying a longitudinal momentum fraction of the moving proton X with a particular energy scale, basically called Q. And the idea is by doing these measurements, these DIS measurements, you can begin to try to map and understand these statistical distributions and get an understanding of how these different kinds of quantities, how these different kinds of quarks, that is, are actually distributed inside the proton and build up, in this case, basically a one-dimensional picture of what the proton really looks like in terms of these internal quantities, these quarks that I keep mentioning. That tells you about the quarks. I mentioned that there was this approximate scaling idea, this notion that basically the scattering cross-section is more or less independent of the energy. It's more or less independent of the energy. In fact, there is another exchange boson, not unlike the photon, but it's essentially the carrier of the strong interaction, the strong force, the so-called gluon, which can then be exchanged among these charge cores, the quarks, and essentially are responsible for radiating momentum and exchanging momentum, and leads to the approximate dependence on the momentum scale in these kinds of DIS experiments. And so the idea is that you can perform a very wide range of measurements at a facility like Hera in Germany and measure this DIS scattering cross-section over a wide range of energies and over a wide range of momentum fractions, essentially. And from that knowledge, you can unfold both the distributions of the quarks, and from knowledge of basically the momentum scaling, you can try to learn about the gluonic content of this object, of these protons as well. Now, how exactly is it that all of this sort of hocus pocus works? It's in fact a complicated story. but it's one that I think is worth mentioning just very briefly. It works because of the very incredible properties of the underlying theory of the strong interaction as we now have it, the so-called theory quantum chromodynamics. And for the students in the audience, for instance, who have taken a little bit of quantum field theory, what we would say formally is that this theory, QCD, the beta function of the theory, which dictates essentially how the strength of the QCD interaction changes with the momentum scale, that beta function is in fact negative. It's just the opposite of what you would find in quantum electrodynamics, the quantum theory of electromagnetic interactions. And the idea is that we can in fact use this remarkable property and something we call QCD perturbation theory to actually write the quantities that I was just showing down in a so-called factorized form. And very much like separating the yolk from the rest of the egg, we can separate away the probabilistic distributions, these PDS that I was just talking about, away from the rest of the description of the deeply inelastic scattering process. And so the idea is that a remarkable property of QCD, the so-called QCD factorization, allows us to describe at very high energies interactions of quarks and gluons in terms of perturbation theory, where basically I write down diagrams, so-called Feynman diagrams, to describe that process. And then the low energy dynamics then are completely encapsulated inside the so-called PDFs that I was just talking about on the previous slide. And the fact that this is something that we can do is really deeply connected to what happens with the interaction of QCD, this alpha strong quantity that essentially becomes smaller and smaller at bigger momentum or bigger energy scales. Now, the fundamental question that really animates a great deal of activity in this field is how is it that QCD, this fundamental theory that we have, which works very, very effectively to describe high energy interactions at places like the Large Hadron Collider, why does that theory that works so well, how does that same theory, when you go to very small soft energy scales where it becomes essentially non-perturbative, where the strength of the QCD interaction becomes very large, how does that theory exactly give rise to this incredibly complex landscape of bound state particles, of things like protons, neutrons, things like pions? How exactly does that really work? It's a very fundamental problem, and in a way, it's very much the chief motivation for a lot of the activity in this field. And it's really, I would put to you, the central question in hadronic physics, as I started my talk saying. So this question really was good for a Nobel Prize, actually. These three gentlemen that I showed on the screen just a moment ago, about 16 years ago. So the question is, if that was good for a Nobel Prize circa 2004, where exactly will this field find the next Nobel Prize? And what I'd like to do is be a little bit provocative and suggest that one possibility, at least for this, is a futuristic machine that is now being discussed in this community and is in fact going forward. And it's what we heard mentioned earlier, just when I started my remarks. It's the so-called Electron-Ion Collider, the EIC, which I'll be talking about a little bit later in the talk. A lot of you perhaps have heard the news about this facility. It was, if you'd like, sort of green lit a little bit earlier in the year, back in January. And we're expecting this to move forward on the scale of the next decade plus. And it's very much, I would suggest to you, sort of the banner activity for this field. It's something that will weigh in at about $2 billion-ish plus or minus on the scale of its construction, which should hopefully complete more or less in the early 2030s if all goes well. And the very important point also that I would like to leave with you is the fact that this facility is really the only next big machine that's planned for construction in this country on the scale of the next 50-ish years or so. And as such, it really will be a centerpiece of activity in both this field, this hadronic physics field, but it will have repercussions far and wide up and down the energy spectrum, as I started saying, including in high energy physics. And I'll get to that point a little bit later in the talk. And the idea of this facility is that essentially a mix of next generation advanced theory and perhaps some novel computational methods like artificial intelligence and machine learning will allow us to peer deeply inside these hadrons in a way that is unprecedented, with unprecedented precision and unprecedented clarity. So this is something that is very, very exciting and coming at us now quite rapidly down the pipeline. So that's something that I'll get back to a little bit later in the talk, and that's the exciting future of this area. where are we now, roughly speaking? So we've learned now quite a lot. Going back to the first slide that I showed you a number of moments ago, that started with Democritus, for goodness sake. We've learned quite a lot about these hadrons and nuclei, and we've found that they have actually an incredibly rich substructure. That substructure, again, I would like to emphasize, can be encapsulated, at least in a one-dimensional sense, by these PDFs that I mentioned, these probabilistic distributions that tell me, again, how exactly is it that a quark Q with a particular flavor, which I'll explain in a moment, carries a momentum fraction x of the proton at a defined energy scale Q. I ask that you try to remember that point because it's quite important. What we found is that these PDFs, in fact, yield a much more complicated picture than anyone might have expected, say 50-ish years ago. Even if I'm being quite schematic, what does the proton really look like? Well, essentially, it's made up of 3 bound valence quarks with a particular flavor, in this case, 2 up quarks and a down quark. But then those 3 valence particles exchange gluons among them, and those gluons actively participate in the structure of the proton. And those gluons as well are soft objects in the sense that they are radiated with they tend to be probabilistically radiated with a very, very low momentum, for instance, of the proton, and then can generate quark-antiquark pairs, the so-called C-quarks, basically. And what happens is that probabilistically, these PDFs, again, being schematic, look something like this, where the high X structure of the proton is dominated by the valence content, which is to say that these PDFs basically, as you go toward large fractions of the proton momentum, what's really going on is that these valence UUD quarks are dominant, whereas toward low X, the C quarks tend to be dominant. Not shown on this plot is the gluon distribution, which would be peaked essentially at very, very low X. What happens, of course, is that now we have a very broad array of standard model particles contributing to the structure of this object of the proton. So this particle zoo of still more fundamental objects, the up-down strange charm quarks actively contribute to the structure of the proton. But in a sense, so do these other particles as well. They're the antiquarks, as well as the gluon and the photon. I won't be able to unpack this whole thing in the course of this talk, but this is the gist. And what I would leave you with is that the hadrons are in fact really a mess. They're incredibly complicated. So essentially what we would like to do is begin to dig inside this very, very convoluted picture and understand what is actually going on inside the proton. You have these up and down quarks, they're exchanging gluons, emitting C quarks, they're somehow rotating and giving rise to the properties of the proton. We would like to actually understand that in a systematic fashion. That's really the issue in this field. Now, what we do, my colleagues and me at Southern Methodist, as many of you certainly know quite well, we perform so-called QCD Global Analyses or global fits as one recourse to try to understand these various distributions. And basically what these analyses do is they operationalize, you'd say, the physics that I just talked about into basically doing some big fit where I actually let the data teach me what these various distributions look like. Now, what the PDFs actually are, they're actually matrix elements. And I've written this very technical looking equation on the slide for you. Don't be alarmed by it. For instance, the students in the audience, basically what this is telling me is that the PDFs are essentially a matrix element, very much like the ones that you might compute in your graduate quantum mechanics course. Essentially, it tells me something not completely unlike an expectation value to find a particular quark inside the proton wave function, basically. And that matrix element essentially is related to what I was just talking about on the previous slide. It's a probabilistic distribution, as I was just saying. The issue, however, is that it's extremely challenging to compute these quantities from first principles, as we would say. That is, if I were to, for the people in the know in the audience, if I were to write down the QCD Lagrangian itself that dictates the fundamental theory of the strong interaction in its full hideous glory, going from that expression for the Lagrangian to then these kinds of distributions that I was just talking about is incredibly non-trivial. And in fact, it's deeply, deeply challenging. There are some recent developments to use an approach called the QCD lattice that are encouraging. And I'll get back to that very briefly, time permitting. But what we instead do is what I started saying just a moment ago. We write down basically parametric forms for these distributions and try to parameterize them in as flexible a fashion as possible. And so the idea then is what I do is I write down these PDFs with some sort of very flexible parametric form, let the data teach me what's going on. And I write these parameterizations down at something like a starting scale for the fit, typically at some soft order GeV momentum scale. And then what I started the talk talking about with the factorization, the QCD factorization, if I have these parameterizations at a starting scale, and I know the fundamental theory of QCD very well, then I can essentially let perturbation theory tell me as I evolve upward how to basically predict processes at places like the Large Hadron Collider or at in DIS, as I was saying. And so the idea is that I want to learn basically what this fitting form is, just as you might do in say, a lab course where you take some data and I'm told that I'm supposed to use some sort of parameterization and I want to fit that parameterization to this data. We want to learn basically what these PDFs are really systematically. And in principle, what you'd like to do is have as much data as possible. So what we aspire to do is really fit the world's data from a very diverse range of scales and processes. And when I say the world's data, I in fact mean a very large amount of data from a variety of sources. I won't unpack all of this, but I leave it to you that basically what we do is we try to get as much data from various kinds of experiments, including the Large Hadron Collider at sort of large momentum scales. That's up here at the top of this plot, which represents all of the data that we fit in a recent global analysis as a function of the momentum fraction I was talking about and then the momentum scale Q. This data lives in this space, and there's many types of different experiments that we would try to describe, including the Large Hadron Collider, including data from the last deeply inelastic scattering collider, so-called HERA that I mentioned a moment ago, and then various other experiments as well. We try to gather all of this and describe it simultaneously and learn these one-dimensional distributions. Now, the result of doing so is something like what we've produced with our colleagues at SMU very recently, the last iteration of one of these so-called global PDF fits or analyses. This is the CT18 global analysis, where after taking all of these ingredients that I just talked about, boiling them all together, what emerges is a detailed picture of basically how the momentum of the proton is distributed as a function of this momentum fraction x that I was just talking about. And this is at something like a scale very close to the starting scale where we fit, as I was just talking about. And you can see that there's really a kind of tangled ball of various quark flavors represented by the various colors. So there's the up quark, the down quark, and various other so-called flavors. And what you should notice is that some of these curves have basically a central line and then a haze about them and an uncertainty, basically. And things like the up quark, this blue, for instance, has a really relatively narrow uncertainty. But things like the strange quark, for instance, this green, is very much less well determined. It has a very large uncertainty. We still don't really have the best handle on it. And so this is something like our present knowledge in one dimension of what's going on. It's a deep picture. It's huge progress has been made, but there's still quite a lot of open questions about what's going on in detail. So what I would put to you is that despite all of this progress that I've described in the first half of this talk, basically, there are numerous fundamental questions that still persist in this field. There's no way that I can hope to give you a complete picture of all of them, but what I would like to do is just take 5 or 10 minutes to give you a very quick survey of some of them, of what's going on basically in this field. So I'll just basically take a moment to briefly survey a sampling of these different basic issues. And what this amounts to doing is really digging into the guts of this basic picture that I showed a number of slides ago, basically looking inside this sort of heuristic picture of the proton and trying to understand what's happening. And trying to understand what's happening entails basically understanding things like the fundamental origin of mass of these particles, disentangling the flavor structure, that is the different types of colored lines basically that I showed on the last slide, answering things, what is the strange, the charm, content, and so forth of the proton, and then doing analogous things. For instance, trying to understand the structure of the pion, trying to do something for nuclei as well, and understanding the emergence of other bulk properties of these particles. So just to give you an idea of a couple of these very briefly, I won't spend much time on any of these slides. Why, for instance, have you asked yourself, do you weigh something rather than nothing, or for that matter, almost nothing? It was in vogue circa 2012 to say that the Higgs mechanism was primarily responsible for this. In fact, that's not really quite the full answer. And in fact, it's not even the majority of the answer. The Higgs mechanism accounts for very little of the mass of the visible universe. And again, by visible universe, I'm talking about hadronic matter, protons, neutrons, the nuclei that make up the bulk of what we're made of, basically. The full answer, in fact, and the preponderance of the answer comes from QCD again. It's actually the dynamics of gluons circulating in that complicated picture that I just showed you a number of moments ago that's really responsible for something like 99% of your mass, basically. So now you can blame QCD rather than last night's dinner for what you behold when you step onto the scale this evening or tomorrow morning. What we would like to do, though, this is a basic sort of heuristic picture of what's going on. We would like to have a very systematic understanding of this. Basically, if I were to decompose the mass of the proton, for example, into various constituent sources coming from the quarks or their angular momentum or these kinds of things, we would like to really understand this systematically, where this mass comes from among the quark-gluon constituents of the proton. And it turns out part of that question is understanding things like these PDFs that I was just getting at. They're related to basically numerical moments or integrations of these statistical distributions. That's one example we would like to understand. I mentioned that we seem to have a fairly good handle on things like the up and down quarks, what they contribute to the proton, whereas we don't have the best understanding of the so-called strangeness contribution of the proton. This has really been a stickly problem for quite a long time in this field. It's one that I've worked on in a number of different contexts. That's to say that the quark C of the proton remains, in general, relatively poorly determined. There are various ways of trying to access this information, the so-called form factors that I just started. And it turns out there are ways that you can relate those form factors to the strangeness PDFs that I just talked about. And this is something that I've worked on with my colleagues, for instance, in Seattle. The point that I wish to give you, though, is that the data in this field is still simply not precise enough, which really directs our attention to next generation experiments like the Electron-Ion Collider. I proposed a measurement to do this at JLab, but again, the precision is not quite there yet. That's the strangeness. There's also things like the heavy quarks, and the first of the heavy quarks, the lightest of the heavy quarks, is the so-called charm quark. The charm quark actually has a mass that's somewhat larger than the mass of the proton. And the question is, what role does the charm quark play in governing or contributing to the dynamics or the structure of the proton, if anything? This is, again, a very fundamental question, and it really gets at what's going on in QCD. We can't claim victory in QCD if we don't actually have an understanding of this issue. And at present, again, we don't quite have sufficient data to really constrain this to our satisfaction. It really points to the importance of future experiments like the EIC. There are other things like patterns of flavor symmetry breaking in the quark C. For instance, these C distributions that I mentioned, the anti-quark distributions, there's the U quark and the D quark, but then there's the anti-U and the anti-D quark. And basically what we would expect is that high energy QCD at sort of asymptotic, very large energies would lead us to expect that basically the anti-down and the anti-U should be more or less exactly the same, that you'd have basically a symmetric quark C in the proton. That's the case, but we're also aware at the same time of non-perturbative dynamics that take place inside the proton. For instance, mechanisms like pion exchange. Pion is a quark-anti-quark pair that can actually play a role in breaking this symmetry that I just talked about. What happens is basically the proton can spontaneously oscillate into, for instance, a positively charged pion that has a valence content of a U and an anti-D quark, plus a neutron, which would actually lead to some breaking of the D bar equals U bar. And there are promising ways of trying to look for this in a number of experiments that we've looked at, like Sequest, that's upcoming with my colleagues inside the CT group. So this is another question where we're really looking for answers and where we are craving more data to try to get a real understanding. I mentioned the pion. What about the pion? We don't have really much of any understanding of what's going inside. We understand the proton, it turns out, much better than we understand the pion. And that's in spite of the fact that the pion is very, very fundamental. It's essentially the effective Yukawa carrier of the nuclear force. And for the more technically minded in the audience who are interested in such things, it also essentially is the pseudo-Goldstone boson in QCD that results from the breaking of chiral symmetry. It's a very fundamental object in the context of QCD, but we don't know what its internal dynamics look like. What essentially are the quark-gluon structure? What does this look like inside the pion? We don't know. On the basis of theoretical models, I've postulated a number of experiments to take place. One of them is going to go forward at JLab, and something analogous is likely to take place at the EIC again. So you notice there's something of a refrain that the EIC is one possibility to really make progress on these questions. I mentioned the pion playing a role inside nuclear structure. What goes on Earth inside the nucleus now? The nucleus, again, is more or less what we're all made of. What exactly is going on inside the nucleus? What happens to things like the protons and neutrons once they're embedded inside this nuclear medium? Does nothing happen? In principle, you could have thought this a number of years ago. I think this is fairly well empirically excluded at this point. There are other possibilities as well that we hope to answer through a combination of theory and experiments. Perhaps more or less the protons and neutrons dissolve into a kind of uniform mean field, or perhaps they form sort of short-lived correlations inside the nucleus as depicted in this kind of artistic cartoon at the top right. Or maybe something else altogether happens. We would like to understand this. This is one motivation of another effort that we're involved with in the nuclear side of things, essentially fitting these PDFs as I just described, but actually for nuclei rather than just for the free proton. Lastly, I'll just gesture at this in passing. There are these questions about where does the bulk structure of the proton and other hadrons come from? And an example is how on earth do you come up with the total spin of the proton? So somehow the quarks and gluons have to combine in some fundamental way to give rise to the total spin 1/2 of the proton. And we would like to understand actually how that works. We are not at all there yet. And so this is another opportunity. So I've given you just a very quick sense for various activities. These are a lot of the sort of pressing questions in this field that I've just been talking about. And what I would argue to you is that we as a field are now approaching the era of really high precision. Just the fact that we're even asking these kinds of basic questions signals the arrival of this era. And what we're doing is moving toward essentially an era of femtoscopy, of something like microscopy, but at the scale of the femtometer that I started my talk mentioning. And really, this is where we're trying to go as a field. We're trying to understand and build systematic, coherent pictures for what does the proton really look like. This is basically answering this question that Democritus posed, the dream of trying to understand at its core, what do protons and other particles really look like? What does nature look like at the finest scale? And this is the central motivation for an enormous number of experiments, really, at places like JLab and current experiments at Brookhaven and at Fermilab, but also at the Electron-Ion Collider, as I'll tell you about in a little bit. So that's a lot about sort of hadronic physics and the open questions in this field. What I'd like to tell you is that these questions, as much as they're very deeply interesting in their own right, they are also very, very important in a number of different directions. And in particular, they're very important at high energies and in the quest to try to understand what might be going on beyond the standard model of particle physics. So this is now more in the direction of the high energy side of things. So a lot of people in our department are very interested in this very basic question, doing things like so-called direct detection experiments to search for dark matter. We know, as many of you have seen in this sort of very, very familiar pie chart, that basically the mass energy budget of the universe can be divided in a tripartite fashion among sort of baryonic contributions, which is what I've just been talking about all this talk, this sort of 4% sliver, something called dark matter, which makes up sort of the rest of 1/4 of the mass energy of the universe. And then the remaining bit, the majority, is dark energy. There's a huge effort in high energy physics and in other areas as well to try to identify what is this dark matter. And what I will argue is that if you wish to try to get at this question, to identify the dark matter, you have to have some handle on this 4% sliver. You have to do better, basically understanding the baryonic matter and addressing the questions that I started my talk really trying to bring up. And I'll concentrate, and where this is relevant is in, well, two areas, but one I'll really focus on is in so-called collider searches, which, as I like to call, is looking for the unexpected in standard model processes. The idea in this case is you can do two different things, basically, and this is being rather simplistic about it. You can perform sort of discovery searches, trying to find dark matter. This is sort of the cave person approach, if I can put it that way, of trying to bash things together at higher and higher energies and look for essentially new content to emerge. This is kind of like what happened in a very rough way with the Higgs discovery circa 2012, sort of searching for bumps or performing bump hunts. That's one approach. There's another related and somewhat, I would say, subtler approach of trying to measure to very high precision various processes in the standard model and look for subtle deviations between what's observed, basically, and what's expected on the basis of the standard model without any of these fancy new ingredients, without any of the BSM physics, as we would say. These are the so-called precision searches, which in a way are not unlike really trying to carefully look for a needle in a haystack, basically, where you're testing the standard model through very fine measurements, trying to find any kind of deviation. Now, the problem, of course, or the opportunity, depending on how you look at it, is that these kinds of searches, at least the collider-based searches, take place at places like the Large Hadron Collider, for instance, where what you're doing is you're colliding protons with other protons, basically, trying to identify the unexpected in that process. And the problem, as you can probably now predict, is that doing these kinds of experiments depends on the PDFs that I was just talking about, of which we have a more or less incomplete understanding. So this equation might look intimidating, but really the point is just that if I want to predict the outcome of an experiment at the Large Hadron Collider, say W or Z production, for instance, then I have to know these quantities in red, which hopefully look familiar to you by now. They are the PDFs that I was just talking about. Everything else I can more or less, depending on my ability, calculate in the context of perturbative quantum chromodynamics or perturbative electroweak theory, as the case may be. But I have to get a better handle of these quantities in red, the unpolarized nucleon PDFs, for instance, as is relevant for activities at LHC. And the issue is that the uncertainties in these PDFs can become really a limiting issue. So for instance, if I want to look for the unexpected, as I was just saying in, say, Higgs phenomenology, it actually really depends what I do at the PDF level. So that's what's written in this case. For instance, the Higgs phenomenology is PDF limited, as we would say. And this can be seen in this just simple table of numerical values. So what do I get for sort of the total Higgs production cross-section, for instance, or really the glue actually dominated channel at, say, next to leading order in a theoretical calculation? What happens is that because of the fact that the dominant mechanism to produce the Higgs goes through gluonic fusion, it really matters basically what PDFs I use essentially and what the uncertainties are. And what you find is that there's really a widespread in predictions. So this is an issue for this field. If we wish to enhance the discovery capabilities of the LHC, we have to try to get this under control and find greater uniformity among these PDF predictions and try to reduce basically the uncertainties that I showed a number of slides ago for the PDFs. So this is what we're really hell-bent on trying to do in this field. What a lot of the world experts are actually at SMU, people like Pavel and Fred and others actually. And what we've been doing in the case of the nucleon-specific effort, the so-called CT effort that I just mentioned, is basically trying to improve our understanding of, in this case, the gluonic structure of the proton. And again, I already showed you something very much like this a number of slides ago. This shows basically our present understanding of the gluonic PDF, or the gluon density of the proton. And ideally, what you'd like to see, if it's to be taken at face value, is a very narrow band, basically. And what we find is that if you go from the last iteration of our global analysis to the more recent iteration, the so-called CT18, or a partner thereof, CT18Z, in the relevant region that's especially important for Higgs production, the improvement in this band is relatively incremental, actually. So the uncertainty band seen here among the different colors is more or less the same. And this again is related to the limitation in improving basically the Higgs physics that I was just talking about. Why is that going on? Now, an essential issue actually comes down to the compatibility basically of the various data sets that we try to describe. So I already gave you a little sense in words for how this works. In a given QCD global fit, we try to describe an array of different fundamental processes and experiments. And what we find is that these various experiments actually will pull things in different directions. So for example, what's shown in this plot is basically how well are we able to describe basically different experiments that in terms of their chi-squared essentially, as I change the value of the gluon PDF at the relevant kinematic region for Higgs production. And what you could say is at the sort of best fit that we prefer, if I dial that value up or down, for instance, some experiments, they have a chi-squared that improves, for instance, or deteriorate as the case may be. But what you'll see is that various experiments have different pulls. Some experiments really prefer, as indicated by this sort of diminishment, a smaller value for the gluon PDF in the Higgs region, whereas others do just the opposite. They prefer a larger value, for instance, experiments with names like E866 that were measured at Fermilab. So that's sort of what's going on. You have these various competing pulls and you have to somehow negotiate among them. And as is the case when you have a disagreement among two friends, you have to somehow be more accommodating. And in a way, what happens is that the PDF uncertainty is enlarged to encompass these various tensions that we find. So this is something that goes on. And another remarkable thing I would point out is that actually what we find is that relevant for Higgs phenomenology, there are experiments that are not at the LHC that do play a very important role. Things like E866 that I just mentioned. This is fixed target Drell-Yan that was measured at Fermilab, for instance, or even neutrino scattering data, for instance. So this is something that I would ask you to keep in mind going forward. I'll just very quickly sort of pass over this issue since my time is getting kind of short. What I would put to you is that a lot of what I'm saying about the importance of understanding the hadronic structure to get better control over high energy physics really goes through as well to activities in the neutrino frontier, as it's often called in this area. So for instance, there's a very crucial kind of centerpiece effort at Fermilab in the intensity frontier to look for neutrino oscillations, for instance, where basically you have a neutrino beam that impinges on a so-called near detector, and then downstream, really a great distance, say hundreds of kilometers, is a so-called far detector. And what you would like to do is essentially correlate activities at these two detectors to see if neutrinos are oscillating or changing flavors, basically, which would be signaled by a disappearance, basically. If you'd like to do that to very good precision, though, you had better understand two things. One is the neutrino flux in these kinds of experiments, and another is the neutrino nuclear cross-section. And you would like to understand the latter object, which I've starred because it's most immediately connected to what I'm talking about in this talk. You would like to understand this in terms of basically the constituents of the nucleus again. So there are two quantities in this case. There's a quasi-elastic form factor related to what I was just talking about at the start of the talk. This is something like an elastic form factor. And then there's the nuclear analog of the PDFs I was talking about, so nuclear DIS distributions. So we would like to know both of these in principle to be able to compute and understand and predict the nuclear cross-section very well. What I've done with some of my colleagues is we did a calculation basically looking into this, basically taking different scenarios and different realistic model calculations basically for the axial form factor. It's a type of elastic form factor basically, and feeding it through a bunch of theoretical machinery, for instance, to predict this neutrino nuclear cross-section. And I won't go into it at great length, but the point is that actually it really intimately matters basically how well you're able to describe these kinds of form factors and how well you're able to then predict the neutrino nucleus scattering and in turn empower basically your search for neutrino flavor oscillations. So this is something that has to be gotten under control as well, just in the same way as the PDFs that I was talking about for activities at the Large Hadron Collider. It's the exact same story once again. You have got to get this under better control if you wish to obtain sort of next generation percent level or sub% precision in these kinds of experiments. So what I would like to do in the last few slides I have for this talk is put to you, I've told you a bunch of problems basically and why you should care about these problems. What I would like to hopefully do is end on something of a positive note and suggest that what we're really doing is approaching what I would consider a kind of golden era in this field, a sort of renaissance where a lot of the questions that I just mentioned that are very profound and sort of at the heart of the question of what is strongly interacting matter and so deeply relevant for high energy physics and low energy nuclear structure, all of these things will soon be addressed in a new and very deep fashion. And they'll be addressed by a convergence of things. One is sort of theoretical developments, one is futuristic novel experiments, and lastly, I would suggest there's a role to be played by next generation computational tools in the form of artificial intelligence or other methods. I'll just mention this very briefly because I don't quite have time. As far as theoretical methods are concerned, what we're moving toward in this field is building really a picture of the multidimensional picture, a multidimensional structure of the proton. These things like the PDFs and the form factors that I was just describing are really just one-dimensional distributions. But obviously, a thing like the proton exists in four-dimensional space-time. It has to have a multi-dimensional structure. And the idea in this field is that we can begin to unfold that multi-dimensional structure through sophisticated new theory in a way that actually is related to things like the PDFs that are important for the high energy experiments I was just talking about. If there's interest, I can talk about this a little more. That's futuristic theory. The next step that I want to talk about, though, is the so-called EIC, this Electron-Ion Collider. And here I really get to the point as far as this much is concerned. So the EIC is something that's enjoyed a great deal of support in this field in the past 20 plus years. It's been really ratified by a number of sort of governing documents, if you'd like, in this area. And the essential questions that this field has really identified for this machine in the official literature, if you'd like, are questions like, what is the origin of the mass of the universe, or the nucleon mass or spin? What exactly goes on inside the nucleus? Can we try to form a multi-dimensional understanding of the proton? If these questions sound familiar to you, they really should, because I already spent a great deal of time telling you why they're so important. So the idea is that this facility is really aimed at exactly these kinds of basic questions and will play a very important role in answering them. How will it do that? It will do that in as much as it's a high luminosity, deeply inelastic scattering collider, very much like Hera, for instance, that ran through to circa 2007, for example. And this facility will be sited at Brookhaven National Lab. And what it will do is it will do the very fundamental sort of clean process that I talked about a number of moments ago, sort of electron or perhaps positron scattering on protons or nuclei at a broad range of energies that will allow us to try to unfold what's going on. And also important, it will collide polarized or unpolarized protons with polarized or unpolarized electrons, as well as light nuclei. It will also measure the structure of unpolarized heavy nuclei as well, and really get at extremely high precision by having a very bright beam, if you'd like. Again, it's just something like 100 to 1,000 times the luminosity of the Hera experiment. So this will be an unprecedented precision and unprecedented kinematic sweep. What we're doing right now is trying to design and optimize this machine. It's an ongoing effort, the so-called Electron-Ion Collider Yellow Report effort. The idea is to try to target this machine toward the most impactful physics. And this is something that we're in the group at SMU obviously deeply involved with. What this picture is meant to encapsulate is basically as a function of the collision energy, depending on basically scenarios for the detector at this place, you can in principle try to aim at different types of physics. So for instance, a certain type of detector, such as we'll expect at ERIC, might be very well adapted to try to measure sort of high energy QCD processes like jet production, for instance, with high luminosity toward the higher energy end of the spectrum. We'd like to understand this in better detail. And so this is a central aspect of what's going on inside this Yellow Report effort. Needless to say, for the sake of this talk, and I can come back to it during the Q&A in a couple of minutes if there's sufficient interest, the impact of this machine, again, will be absolutely off the charts. Will be very, very large, and it will very rapidly outdistance a lot of the data that we already have and use to constrain things like the PDFs. So that's what's shown in this left panel, for instance, that basically the result of fitting Electron-Ion Collider pseudo data will go beyond much of the most constraining data we already have only in something like a year. We can also do all kinds of other measurements at this facility. We can measure things like charm production in a way that might allow us to unfold the strangeness content that I mentioned before as being so problematic. So there are lots of opportunities of sort of aiming this at high energy physics. And this is also playing out inside the SNOMAS 2021 proceedings as well. And we would very much like this message to be incorporated. I'm going to go ahead and skip this because I don't quite have time, but what I would just mention in words is that there's also a novel method, the so-called lattice QCD approach to actually computing the PDFs from first principles from the QCD Lagrangian that will be very much relevant in the EIC era as well. And if there are questions, I'm happy to sort of circle back to this. Now, the last couple of minutes, what I'll just quickly do to end the talk is mention that there's another aspect to this story, which is the advent of what I would call the big data era, which is really already, I think, at the door. As you can see from this plot, just on the high energy side of things, sort of the takeoff in accumulated data as a function of time. We're sitting somewhere around this red star. The blue line really takes off on the scale of the next decade or plus. And so we have an enormous amount of data coming in, which is going to be very, very challenging to make sense of. As much as it's also exciting, it will be deeply problematic because it's very much like drinking from a fire hose of high energy physics data. But what I'd suggest is there are multiple ways of doing this. There's an inelegant way of trying to drink from a high energy physics data fire hose, something like this, of basically having no plan. There's another way of sort of siphoning off some information and trying to capitalize on it, which is shown in this case. But of course, you lose a great deal of the information. What we would really like to do, however, is exploit the full magnitude of the data set, which is something like an inverse attobarn, something like 1,000 inverse femtobarns, for those who are familiar with such terms. And what I would argue is that it's sort of a convergence of methods that will hopefully help us deal with this enormous amount of information flying at us. One is additional experiments, like the EIC, as I was just saying. One is next steps in theory, basically moving our description in terms of theoretical physics to a next level of precision, which I'd be happy to talk about. But another is sort of machine learning or advanced statistical techniques, which I'll just gesture at. Let me just go ahead and hopefully this will work. One thing that we've been doing, and I am just about done with my talk, one thing that we've been trying to do is learn what we might be able to achieve with various machine learning algorithms to try to extract properties from the enormous amount of information we have at our disposal. So what we do in the context of these global QCD analyses, as I mentioned, is describe thousands of data points, basically, from all kinds of different experiments. And so we exploit, we've been investigating novel methods, AI methods like dimensionality reduction, including the so-called TSNE, T-distributed stochastic neighbor embedding, which lets us learn properties in principle of the data set. And what is being shown, for instance, in this plot is a representation, actually color-coded, of all of the data that we fit in a typical QCD global analysis, sorted by physical process. There's the DIS data, like neutrino scattering information like NuTev, Drell-Yan data, and then the LHC data in sort of pink or magenta. I'm just showing this in a three-dimensional representation. What then happens is we start this machine learning algorithm, which essentially does a kind of mapping. It's mapping this data that lives, in fact, in a very high dimensional space and tries to map it to a most efficient sort of three-dimensional space in a fashion that begins to learn some of the properties of this data. And the remarkable thing that's occurring that hopefully is jumping out at you is we started with a sort of undifferentiated mess of points that's now beginning to sort of aggregate and form patterns, basically. And essentially what the algorithm is doing with no input from us really, other than just providing a description of these data points in terms of the theory, it's learning essentially which points belong to which physical process in a very intriguing way. So we're very eager to try to exploit this sort of technology to understand and get at underlying information that might otherwise be very challenging to extract from the QCD global fits. So this is an example of where we hope to go in the near future. Now, there are various tools. That's just an example. And in fact, there are quite a number of opportunities in this area for artificial intelligence and machine learning and various other novel statistical methods that we've been exploring, including in the group at Southern Methodist University, novel methods for parameter selection and estimation, model differentiation, sort of fast statistical methods to try to learn what's going on from different experiments, these data embedding methods that I just mentioned. There's a lot of activity in this area. But what I'll do is end on a kind of cautionary note that having all of these tools is really advantageous, but they're to be regarded just as that. Essentially, they're tools, and it's hopefully helpful to have them in as much as it helps us to avoid sort of common pitfalls. But again, what I wish to emphasize is that it's really a simultaneous convergence of different methods that's most helpful. So for instance, machine learning does very well in principle. It does good at sort of learning pictures of dogs, like our dog, for instance. But sometimes it makes mistakes, for instance. So Google Images is convinced, for instance, that this picture of my dog and this picture of this washer dryer are actually the same. Of course, they're not. So the lesson, the takeaway from all of this is that machine learning by itself might be helpful, but it's not the whole story. And again, we want an array of the methods that I was just talking about in this presentation to make progress. So with that, I come to my conclusions and make just a quick comment about where we're going. So I hope I've left you with the impression that this field is really at a very exciting moment. There's all of this new information coming at us, new theory, new computational tools, futuristic experiments like the EIC coming at us. And again, what I want to really stress is that this activity will have very, very profound implications for an array of other investigations, both in nuclear and particle physics. And really now is the time, if you're interested in these problems, to try to dive in, because we're at an early stage still where things can still be shaped and guided. And there are numerous opportunities to work on this, numerous exciting possibilities, all kinds of ideas for student projects and chances to collaborate on fundamental problems. And also many institutions are jumping in, as I've hopefully told you during the course of this talk. So with that, I will just thank you very much for your attention and would be happy to take any questions if there are some.
Yeah, okay, great. Yeah, thank you very much, Tim. We'll give you a little canned applause here to simulate.
Hey, thank you.
4 times.
Yeah, great.
We all remember what that actually sounded like.
Yes.
Right? Okay, so again, if you want to ask a question of Tim, please just go ahead and type the word speak in the chat window. We'll give you a few seconds to go ahead and do that. And absent that, Pavel and I will just use chair's prerogative to ask questions. I have a couple of things I jotted down.
You bet.
Yeah. All right, well, so to get things kicked off, Tim, if you don't mind me asking a question.
Please do.
So, I mean, you talked about using large-scale machine learning techniques to, for instance, explore a high-dimensional space and find clusters.
That's right, yeah.
Yeah, another thing that you touched on that presumably is also intensely computational would be this first principles calculation of parton distribution functions using lattice QCD methods. Could you talk a little bit more about that? What are the challenges there?
The challenges are very, very deep, and there's a very extended community that's dedicated to this kind of activity. I'll just go to this slide just so that I have something to gesture at, sort of. Yeah, the idea, and maybe I can sort of say a few words, especially for students or non-experts in this particular area. The idea is, again, this issue of QCD as being non-perturbative at soft momentum scales or at low energy, where the coupling of the theory becomes so strong that I can't practice my usual perturbation theory techniques of writing down a bunch of Feynman diagrams, adding them up in a fashion that is perturbatively under control, basically. What instead is done in this case is one does a calculation on the QCD lattice, where what you do is you implement basically a finite discretization in a Euclidean 4-dimensional space-time and write down, Euclideanize the QCD Lagrangian and write it down and essentially compute on this finite sort of lattice work the basic theory. And so you can then compute basic matrix elements in this discretized space-time, where basically the size of the lattice, so the size of the lattice spacing and the size of basically the box that you can do the calculation on act as basically regulators of either the ultraviolet or the infrared, respectively. Now, the problem is that that is indeed extremely computationally expensive. So a typical calculation would be historically to calculate actually just single value matrix elements, things like the moments of the PDFs, for example, or calculating some charge, for instance, of the nucleon, these kinds of things. And it would be a millions of CPU core hours type calculation that would be submitted and run for months at a time in principle. What's going on now is there's another way of doing the calculation, what you'd like to do is actually extract the X dependence to actually get the one-dimensional distributions that I spent so much time talking about in this presentation. The problem, of course, is that if you have a Euclidean spacetime, it's actually not defined to compute a finite spacetime separation of quark fields in the Euclidean spacetime in the usual technical definition of the PDF. So what you can instead do is calculate a slightly different matrix element. And that leads to this quasi-distribution, for instance, that we plot here in this bottom left panel. So that's something that is being developed. There are a lot of theoretical issues with it as well. For instance, you have to have a kind of formal matching, very much like what is done in perturbation theory for HEP experiments, where you identify or map basically the actual proper PDFs to these quasi-PDF distributions. And they're related by perturbatively calculable coefficients, basically, that are still being developed and are really only known for select distributions like this isovector U minus D type distribution, say to one loop order, or perhaps under some circumstances past that. So there are a lot of problems just on the pure theory side. And then on the side of the computation, it's the fact that it's very expensive. And then there are also various so-called lattice artifacts that come into the calculation that also make it deeply challenging and problematic. So the serious practitioners of this field spend an enormous amount of time trying to get those under control. But it's an exciting area, and it's indeed picking up steam in a way. And so the hope is that on the scale of perhaps a decade, once the EIC is really underway, that there could be a kind of synergy between the two. Where, for instance, the EIC might take high precision data that might serve as benchmarks, for instance, to some of the lattice calculations and give us a little more confidence in them. And the lattice calculations might be able to access regions of the PDF that are challenging to extract from data that may or may not actually have sensitivity to that region. So there's a lot of activity in this point that I think is really a source of excitement.
Okay, yeah, no, thank you. Are there any other questions?
Okay, can I ask a question since I'm unmuted?
Oh, of course.
So Tim, well, you described all this amazing program of studying the structure of the protons, or also other particles. What is your favorite physics question in this area? Maybe again, so if you were to tell to our students who are looking ahead, like in a few, well, they essentially try to choose the topic for their thesis.
Absolutely, yeah. So
what excites you in this? Like,
so there are many instances. So I hopefully I can maybe say a couple actually, because it's a manifold problem, multifaceted problem. I mean, there's a big question, which is the one that I mentioned to start the talk, or at least a few slides in, which is, again, we have this theory that works very, very well to describe what's going on at the Large Hadron Collider. It's in principle, in as much as I'm able to compute to nth loop order or whatever, it's in principle, it's very challenging, obviously, no doubt, but I can in principle do a calculation in that case, and things work very, very well. The question that is so interesting, and I think what attracted me to this field and what has really driven me, the big question, is again, how exactly is it that that same theory that works so well, and how does that same theory give rise to this emergence of various phenomena at lower energies? That same theory that is so well under control and works so well to calculate the outcome of high energy physics scattering experiments is a devil to compute at the scale where it actually is responsible for governing the properties of the proton, for instance. And that's just a deeply fundamental question. And it's really at the heart of this field. There are a lot of other questions that sort of are ramifications of this that emanate out of it. And hopefully I posed a number of them in this talk. I mean, things like patterns of flavor symmetry breaking that I mentioned in this talk that I think are very, very deeply interesting in their own right, just intellectually. I find it very, very just appealing that these kinds of questions where, okay, there's some sort of very elaborate dynamics that's taking place that's responsible for breaking the ideal symmetry among the different quark flavors, say in the quark C. there's some sort of elaborate dynamics that's responsible for that pattern of flavor symmetry breaking. And again, it follows from this fundamental Lagrangian in a way that we simply don't really understand quite to the desired level of accuracy. And I find that very interesting. And I find it very interesting that simply nature is so complicated at this level. There's no reason, no one in their right mind a generation or two ago would have necessarily expected that the structure of the proton is as elaborate as it turns out to be. It's incredibly complicated, and it all follows from what would seem to be a very simple kernel of the QCD Lagrangians. And that's just absolutely very fascinating and somehow very pleasing. And then the fact that that activity is so deeply related to, for instance, improving precision of experimental searches for BSM physics, for instance, is just, it's just absolutely pleasing that there is a kind of unity in nature and a kind of broad relevance of these questions in so many different areas. So for that reason, I just find it really appealing to students who might be interested, because it's something where once you start drilling down on the physics, you can take it so many different directions, and it's so deeply relevant in so many different ways that I think that's very exciting.
Okay. Yeah. So we're quite a bit over time, and we don't seem to have any more questions. Last chance for somebody, I guess, other than the moderators to jump in and ask a question. Give you a few seconds here to type speak in the chat window so we can unmute you if you want to do that.
And thank you for indulging me in going, I know, a little bit over.
No worries. Okay, well, it looks like we don't have any more questions. Tim, you must have given a fantastic colloquium. So we'll see what questions the students ask you.
And you know, everybody in the department, I hope you know me, you know my email address. So if you would like to have a one-on-one Zoom chat, anything caught your attention, or you'd like to have some references about interesting papers or something to get started on any of these questions, I would only be happy to chat further. Okay. So thank you so much.
No, that's excellent. Thank you, Tim. Okay, well, with that wonderful end note, let's go ahead and close out the event for today and thank the speaker one more time, and hope everybody has a safe evening. Okay, take care, everybody.
Take care. Thank you.
Thanks, everyone.